Welcome to section 3 of Psych 331 Statistics for Psychologists. In the previous two sessions, we laid the foundation for what the whole course is about. We look at some of the theories behind the figures that we see. We've looked at what we mean by the mean, what we mean by standard deviation, and we also look at variances as well as the standard error of the mean. We went on to look at the various types of tests that we have. That broadly we have two types, parametric test and non-parametric test. And we talk about the distinction between them and the conditions or assumptions that have to be met for these various tests to be run. And so in this section, we will be looking at two key statistical tests. And these are tests that we run when we are dealing with only one sample drawn from a single population, and tests that we run when we are dealing with two samples that we have randomly picked from two different populations. So the goal of this section is basically to equip you with the ability to differentiate between the parametric test and the non-parametric test. It's also to equip you to be able to analyze data that has been collected from a single population, and also for you to be able to analyze data that has been collected from two independent populations. So that is basically what we will be looking at in this third section. In other words, in this third section, we'll be looking at inferences about the mean of a single population and inferences about the mean of two populations. So the key topics to be covered in this section are as follows. One, we'll look at inferences about the mean of a single population. That is instances where we have to use the test called the z-test, and then we'll also look at instances where we have to use a test called the one-sample t-test or the t-test based on a single population. We'll also quickly revise and look at some work examples on the 6 steps that we need to follow in answering full steps questions in differential stats. We'll also look at inferences about the difference between the means of two unrelated populations, that is the independent t-test. And then finally, we'll also look at the correlated t-test, where we want to make inferences about the difference between the means of two related populations. So basically, this is the outline of what will be covered in this section. And we have our key reading list here. That's the book by J.Y. Opoku, Tutorials in Inferential Statistics. And this course, the portions that will be very relevant for this particular session can be found on pages 45 to 84. There are two other books that we need to consult if you want further understanding in this course. So let's start with the first one. What is the difference between the parametric test and the non-parametric test? As we have looked at earlier, that we have two broad types of tests that we can use, parametric test and non-parametric test. Under parametric test, we have various specific tests, and then under non-parametric too, we have various specific tests. So these are just two groups of statistical tests that we can perform on any given data. The question then that we need to address is, when do we run the parametric test and when do we run the specific non-parametric test? One is that we will be permitted to run a specific parametric test if the level of measurement of the dependent variable is at least on an interval scale. It's measured on at least an interval. That means that it should be measured on a ratio or interval scale. Once this assumption is there, then we should be thinking about selecting from the group of parametric tests to analyze the data. And then the non-parametric tests, they do not make any assumptions. Sometimes we call them distribution-free tests. You don't have to have any assumptions measured. So usually we run them when our data is collected on the DV, at least on an ordinal or nominal level. Once we have ordinal or nominal level, then we can run a specific non-parametric test. Let me also explain here that, as we said in the previous section, parametric tests are always preferred to non-parametric tests because they have what we call more power. Parametric tests have more power, and power simply refers to the probability of rejecting our HO when the HO is actually false, and that is the aim of every researcher. That is what we want to show to the world. So since the aim of any researcher is to reject the null hypothesis, that's the HO, and support the research or working hypothesis, it is always advisable to use a parametric test to analyze the data, provided the assumptions underlying the use of such a parametric test are satisfied. So that is basically the distinction between a parametric test and non-parametric test. Now let's move on to look at inferences about the mean of a single population when the population standard deviation is known. Now, if you are conducting a study where you have picked just one sample and you want to find out whether the sample is truly coming from the given population. For example, we want to find out whether the average age of the distance students is actually older than the overall University of Ghana students. So here we have a single sample here being the distance students being compared to all students of the University of Ghana. You realize that the distance students that we have picked is also coming from all the University of Ghana students. So we have a single sample being drawn from a single population. So if our population mean and the population standard deviation are known, then the best test for us to use to analyze such a data is the Z-test. However, if we have the same situation, that is, we have picked a single sample from a single population, but the population standard deviation and the population mean are not known, then we cannot run the Z-test. We need to run what we call the one sample t-test, or the single sample t-test, or the t-test based on the single population, and that is what we have to run. So the Z-test is the procedure for computing the Z-scores for a sample mean on the sampling distribution of means, and this is a parametric test. So by it being a parametric test, it means that the dependent variable, or the DV, should be measured on at least the interval scale. So the Z-test is used to make an inference from a single sample to a single population when both the mean and standard deviation of scores in the population are known. And as I said, the DV should also be measured on the interval scale. So these two things have to be satisfied for us to use the Z-test. They have to be met before we can use the Z-test. So that is basically what we need to know. Know that the true standard deviation of the population have to be there, and then the true mean of the population will have to be there. Now, what is the formula for computing the Z-test? It's very simple. The formula for computing the Z is simply the sample mean minus the population mean divided by the standard error of the mean based on the population. It is the sample mean minus the population mean divided by the standard error of the mean based on the population, and that will give us the Z-score. And how do we treat the Z-score? As we've seen in the previous section, in session 2, that when running, when analyzing data, what we are actually doing is that we are testing what we call hypothesis. And hypothesis, as we explained earlier, are predictions, intellectual predictions that we have made, and we've now collected the data and we want to test them whether such predictions are true or not. We've also gone on to look at the fact that we can have two types of such predictions. We can have what we call two-tail hypothesis or two-tail test, and we can also have what we call the one-tail test. So how do we treat the Z-test under two-tail situation and then under the one-tail situation? Now, under the two-tail situation, what we do is that we first have to create the sampling distribution of means from the underlying raw population that the HO says about our data. Once we create that, then we choose the criterion, which we most of the time refers to as the level of significance or the alpha level. And then we also locate the region of rejection, which for a two-tailed test will involve an area on both ends of the normal curve. In actual fact, the z-test is precisely the normal curve distribution. And so most of the time we use the z-test in explaining how, we use the normal curve in explaining how the z-test works. Then we determine the critical value by using the choosing alpha level, and then we find the z-critical value resulting in the appropriate region of rejection. So in the two-tailed test, the null hypothesis will state that the population means equal a given value. For example, that the population mean is equal to 100. That is what a two-tailed test will state. And then the alternative hypothesis will state that the population mean is not equal to 100. So here, all that we are saying is that, there will be a difference. All that the researcher wants to show to us that there will be a difference between the sample mean that we have drawn and the population mean. As to where that difference will fall, as to whether the population mean will be bigger than the sample mean or the sample mean will be bigger than the population mean, that is not the focus of the researcher. All the researcher is interested in is that there will be a difference. Whatever it falls, the researcher has achieved his or her aim, or has shown to us that the alternative hypothesis, that's the H1, is the case. So that is basically how we state the two-tailed hypothesis. So here, because the researcher is not focusing at one particular end, is just interested that there will be a difference. Such a difference can be on the left side of the normal curve, or it could also be on the right side of the normal curve. And as we have seen earlier, that for us in the social sciences, we always, by convention, adopt the alpha level to be at 0.05. So if we want to illustrate that on the normal curve, then this is how it will show here. Then it means that the 0.05 that we have adopted in the social sciences, which represents 5%, it means that 2.5% will be on the left side of the normal curve, and another 2.5% to be on the right side of the normal curve, which we have illustrated in the previous section. And so this region that we see here is the region of rejection. The 2.5% here is the region of rejection, and then this side will also be the point of rejection. And we have noticed the last time that if we want to illustrate on the normal curve, and we have 2.5% here, 2.5% here, then they will end at 1.95 at both ends. So it will end at negative 1.95 and positive 1.95. So we have these two regions as the regions of rejection. So it means that when we compute our z value, and the z value falls within this point of rejection, either it is less than 1.95, the negative 1.95, or it is greater than positive 1.95, then we are going to reject our HO. But if our z computed, the computed z, falls within this region, that is negative 1.96 to positive 1.96, we will be retaining our HO. So this is how we demonstrate or illustrate the point of rejection and the point of retention for our HO when dealing with a two-tailed hypothesis. We are going to have 2 points of rejection, which will be at the two ends, and that is why it's called a two-tailed hypothesis. The rejection point will be at both ends, both tail ends of the normal curve. And so that's what we have over here. Now, what we have to do is that once we have created this criterion, or we have located the region where we'll be rejecting and then the region where we'll be retaining our HO, then the next thing to do is for us to compute our z-score. The next thing is for us to compute our z-score. And as we have seen in the previous slides, the z formula is simply our sample mean minus our population mean divided by the standard error of the mean based on the population. So it's very simple. What we need to do is how do we compute the standard error of the mean based on the population. The standard error of the mean based on the population is simply the standard deviation of the population divided by the square root of the sample size. The square root of the sample size. So this is the standard deviation based on the population, and then this is the sample size. Remember, we said we can only use the z when our population standard deviation is known and our population mean is also known. So it will be very easy for us to compute this because that will be known from any research situation that is given, any research situation. If we don't know that, or it's not possible for us to compute this, then we have to use the one sample t-test or the t-test based on a single population. So once we have computed the z value, then what we have to do is to compare the computed value to the region of rejection and retention that we have created over here. We have to compare it, and we said that the decision we have to take is that if it falls within this range, we are going to retain our HO. But if it falls over here, we are going to reject HO. If it falls over here too, we are going to reject HO. So that will be the decision. That is the criterion that we are going to take the decision. So if you want to summarize what will be on this graph, if you want to summarize what is on this graph here in line with our computed z value, then this is the decision that we are going to take when we are dealing with a two-tail situation. We will have to reject our HO if the z-score that we have computed is less than or equal to the negative value of the critical z. Or we will also have to reject our HO if the z-score that we have computed is greater or equal to the positive value of the critical z. So basically, that's what we are saying here is this: if the value that we have computed is less than the negative value of what is on this line, that is the negative 1.96, then we will have to reject our HO, and we'll also reject our HO if the z-score that we have computed falls on this line or is greater than the positive of the critical value, that is the 1.96. Then that will be the decision that we'll take. We'll have to reject our HO, and then we will retain our HO if it falls within the range. If it falls within the range, then we will retain our HO. So let's see what the consequences are rejecting or retaining HO. What we are saying here is that when the z observed falls beyond the critical value, then we reject HO and accept H1. That is, in other words, when we reject HO, indirectly we are accepting H1. And when that happens, or if that is what we observe in a research situation, we say that the result is significant. There is a significant difference. Significant here indicates that the results are unlikely to occur if the predicted relationship does not exist in the population. When we say a result is significant, it means that the difference that we are seeing in the results, in other words, the mean difference between our sample population, in our sample mean and the population mean, is not due to chance. It's a real difference. Something real and something interesting is happening. It can never be due to chance. And when we retain our HO, that is where the z observed does not fall beyond the critical value, or it does not lie within the region of rejection, then it means that we have failed to reject our HO, or in other words, we have retained our HO. So anytime we fail to reject our HO, or anytime we have retained our HO, then what we say is that the result is not significant, or the result is non-significant. And non-significant means that any observed difference that we see between our population mean and our sample mean is simply due to chance, simply due to sampling error. It is not anything real that is happening. It can be neglected. So to sum up, some few points to note about the z-test. One, if the z-score that we have computed is large, then the probability that the HO is true is small. And if the z-test is larger than the critical value, then HO should be rejected. And then also, if the z statistics is smaller than the critical value, then HO is not rejected. Or in other words, HO is retained. And we should equally note when we say that the result is not significant or it is not significant, it does not mean that we have proven that our HO is true. No, what it simply means is that the difference between our population mean and our sample mean is negligible. It is simply due to chance, it's simply due to errors. So non-significant results provide no convincing evidence that the independent variable does not work. It could be the case that it works, but in this instance, perhaps the way we have gone about picking our participants to form the sample could have introduced some errors in it there. So that is what we need to know about the z-test when dealing with the two-tail situation. Now, when we are dealing with the one-tail hypothesis with the z-test, then what really happens? One-tail means that here we are specific as to where the difference will be. Remember, when it comes to z-test, we are only looking at two things. We are comparing a sample mean, a single sample mean, and a single population mean. And we said two-tail will tell us that there will be a difference. As to where the difference will fall, we don't know. When it comes to one-tail, we will be specific as to where the difference will be. So we can either say that the sample mean will be larger than the population mean. That is a one-tail situation. Or we could predict that we expect the population mean to rather be larger than the sample mean. These are one-tail hypothesis. We have given direction as to where the difference should fall. So sometimes one-tail hypotheses are also called directional hypothesis. So we expect it to be only at one direction, only at one direction. So if we want to illustrate with the same normal curve, then this is how it works. If we expect, on the left-hand side here, if we expect our sample mean to be bigger than the population mean, then we expect the point of rejection to be at the positive end over here. And remember that this time, because we expect the difference to be at one end, all the 5% to be at one place, there will be nothing over here. Because we will not be looking at any difference here, we will not be expecting anything. We will be expecting everything to be at this point. Remember the formula for the z-test. The numerator is the sample mean minus the population mean. So if you expect the sample mean to be bigger than the population mean, then we expect that at the end we should be getting a bigger value or a positive value. And so that difference should be falling over here. So once we compute and it falls on this line, that is positive 1.645, falls on that line or greater, then we will reject our HO. Anything different from that, we will be retaining our HO, or will be failing to reject our HO. And then on the other hand, if we expect the population mean to rather be bigger or larger than the sample mean, then we will be expecting the difference to fall at the negative end. We will be expecting the difference to fall at the negative end. And this is so because of the formula for the z-test, which is the sample mean minus the population mean. That is the numerator aspect of the formula. So we will be expecting all to fall at this place. So once our z computed falls on this line, that's the negative 1.645 or smaller, then we will reject our HO. Anything different from that, we will be retaining our HO, or will fail to retain our HO. So let's have an illustrative example here. So we have here, use the following data set and conduct a 2-tail-z test to determine if the population mean is equal to 11, given that the population standard deviation is 4.1. So here clearly we have some scores here. We have the first line, we have 6 of them, 6, 6, so we have 18, a sample size of 18, and then we have the population mean here of 11, and then we have the population standard deviation of 4.1. So clearly we can compute our z-score, and then we will see where it will fall and we'll take a decision. So here we have our HO, we state that the population mean is equal to 11, and then H1 we state that the population mean is not equal to 11. And we are stating it this way because the question says we should use a 2-tail hypothesis, 2-tail z-test. And when it comes to 2-tail, what we are interested in is that there is a difference as to where the difference will fall is it's not a concern of the researcher. So we pick our usual alpha level, which by convention social sciences have adopted, that's the 0.05, and then we get our critical value here. Because it's 2-tail, we know that the point of rejection will be at 2 ends. We will be rejecting if our t observed is greater than 1.96, and we'll also reject our HO if our t observed is less than negative 1.96. So 1.96 plus or minus 1.96 is the critical value for the z when we are using alpha of 0.05. So that's what happened. Now let's compute our z-score. Before we compute the z-score, as the formula stands, we know the sample mean. We can quickly compute that from the data that we have there. The population mean is given as 11, but we don't know the standard error of the mean based on the population. So we first have to compute the standard error based on the population. And the formula is the standard deviation based on the population divided by the square root of the sample size. We know the sample size to be 18. We know the standard deviation based on the population to be 4.1. So quickly we can compute our standard error of the mean based on the population, and that becomes 0.966. So with that, we can now compute our z observed. If you look at the data given, if you add all the values that are here and divide by the total number of cases here, which is 18, that will give us a mean value of 13.67. So we subtract our 11 from it, and then we divide it by the standard error of the mean, and that gives us positive 2.764 as our z-score. So we now have to look at this 2.764 and compare it to our point of rejection or the point of retention, and then take a decision. As you can see, our decision rule here, the 2.76 is greater than positive 1.96. So clearly our decision will be here that we should reject our HO. So that means that the population mean is not equal to 11. So since our z observed lies within the rejection region, we reject HO and accept our H1. And so we conclude that the population mean does not equal to 11. In other words, the population mean is greater than 11. As we can see here, is greater than the 11 that we have over here. So that is how the z-test works. The z-test is clearly based on the normal curve. How the z-test works, clearly based on the normal curve. And one of the uniqueness about the z-test is that of all the tests is the number one test that is not influenced by sample size. Whether we have 1,000 sample size, we have 100 sample size, that will not affect our critical value. It is only the alpha level that matters when it comes to the z-test. Later, we'll get to know that all the other tests that we'll be looking at, they will be affected by the size of our sample. So that's about the z-test. We'll move on to look at the one sample t-test, or the single sample t-test. So here, we'll try to address three key things. What is the purpose of the one sample t-test? How is it different from the z-test? And what are the assumptions underlying the use of the one sample t-test? Then perhaps we'll look at some work examples or illustrations as well. So what is the purpose of a single sample t-test? This single sample t-test is used to compare a sample mean to a population mean. So here what it means is that the single sample t-test and the z-test performs the same thing. Both are used to compare a single sample mean to a single population mean. The single sample t-test therefore tests the null hypothesis that the sample is truly coming from a given population. It tests the null hypothesis that the sample, the mean of a given sample, is truly coming from a specified population. So it is used much of the time when we have a one sample research design. When we have a one sample research design, then we will have to use the one sample t-test. Now, how is it different if they are performing the same thing, the one sample t-test and then the z-test are performing the same thing? What is the difference between them? How is it different from the z-test? Now, the z-test requires you to know the population standard deviation. But much of the time, we do not have this information. So if you don't know the population standard deviation, then your best estimate of it is the sample standard deviation. So when we use the sample standard deviation instead of the population standard deviation, then we are dealing with a t-test or a single sample t-test. So the only difference, the key difference between the z-test and the one sample t-test is that in the one sample t-test, much of the time the population standard deviation will not be known. We will not know it. And once we don't know the population standard deviation, we cannot compute the standard error of the mean based on the population. So we have to estimate it from the sample mean. We have to estimate it from the sample information. So comparing the formulas, you can see over here, when it comes to the z-test, it is the sample mean minus the population mean divided by the standard error of the mean based on the population. Now, when it comes to the t-test, we don't know the population standard deviation, so we cannot have this. What we do is that we rather estimate the standard error of the mean based on the sample. So we estimate this using the sample information. And remember, in inferential stats, all that you are trying to do is that we want to use sample information to estimate what will be happening in the population. So it makes sense in instances where we do not have population information, we can't fall on the sample information. If, however, we have the population information, it doesn't make sense for us to use the sample estimates. So what I'm saying is that if you have a research situation and this information is there, the population standard deviation is there, it doesn't make sense for us to use the one sample t-test. We have to use the z-test. But if we don't have it, our only option is to estimate it from the sample, and that is what we have over here. So you can see that is the formula for the two are almost the same. The formula are the same, except that this is dealing with population information. This is dealing with sample information. So that's the difference comparing the two. So how is it different? The t distribution is symmetrical but flatter than the normal distribution. Remember, I mentioned that the z-test is basically a normal distribution. It follows the normal curve. Now, the t-test or the t-test that we have also follows the normal curve, but they don't possess that property of symmetry. The property of symmetry much of the time is not there. They look much flatter than the normal curve. So the exact shape of a t distribution depends on the degrees of freedom. And here is another point that I've made earlier, that the z-test is not influenced by sample size or by the degrees of freedom, but the t distribution is influenced by the degrees of freedom. So unlike the z-test, the t value is influenced by sample size, so that for every sample size, there is a different t distribution. For every sample size, there is a different critical value. For every sample size, there is a different degrees of freedom. So the t tables are therefore read with reference to degrees of freedom, a concept which we have explained earlier, that it is related to the sample size. So if you compare the two, this is how it looks. The z-test looks more of a normal distribution, but the t-test, as I said, look much flatter. It approaches the normal distribution whenever the sample size becomes larger. With larger sample size, you could see that there will be no difference, no significant difference whether you use a z-test or we use a t-test in our analysis. What do we mean by degrees of freedom? Degrees of freedom simply refers to the number of components in any given computations that are free to vary. Number of components in a calculation that are free to vary. For example, if we have 10 numbers that adds up to 40, if you have 10 numbers, if we randomly pick 10 numbers and those 10 numbers will add up to 40, and we want to change those numbers, what it means that we can change the value of the first one, we can change the value of the second, we can change all of them. But when you get to the last one, for it to add up to the number 40, the last one becomes fixed, which means that the rest are free to change, they are free to vary, but the last one becomes fixed. So whenever we are dealing with a one sample situation, the degrees of freedom, the numbers that are free to vary, will be the sample size, which is the capital N, minus 1. All of them are free to vary except one. The last one will not be able to change, because the moment we change the last one to, the value will not add up to the same amount that are there. What are the assumptions underlying the one sample t-test? Just like the z-test, the observation should be independent. There should be independent observations, and then the dependent variable should be measured on the interval or ratio scale, and then the population distribution should also be close to symmetry, or it should be symmetrical. So here we have the formula for the t-test based on a single population, and it is the sample mean minus the population mean divided by the standard error of the mean based on the sample. So the difference between the one sample t-test and the z-test is just the denominator here. Whilst the z-test, it is the standard error of the mean based on the population. Here it is the standard error of the mean based on the sample. So computing the one sample t-test, first what we have to do is that we have to compute the estimate sample standard deviation. Because of the formula, what we have to do is that we first have to estimate the standard deviation, And then from there, we estimate the standard error based on the sample standard deviation, and then we can now compute it. So we compute the sample standard deviation, and then we compute the standard error of the mean, and then finally we compute the t observed. So the formulas are here. That's the formula to compute the standard deviation based on a sample data. And then once we get that value, that is what will come to this place, and then we compute the standard error of the mean based on the sample. And then we have, once we have this information, that is what will come to the denominator here, and then we finally compute our t observed. So it's a very simple 3-step computation that has to be performed: the standard deviation, standard error of the mean, and then the t observed. And then how do we take the decision? How do we take the decision? Taking the decision is similar to what happens in the z-test. So after computing the value of t using the formula, the t observed value is referred to the t tables with the appropriate degrees of freedom. So here to need the critical value. We need the critical value. So like the z-test, the t observed is compared to the critical value of t at the selected decision rule or the selected alpha level, and the decision is taken as to whether we will retain or reject our HO. And as we can see over here, if we are dealing with a two-tail situation, as we have noted in the z-test, the point of rejection will be at two ends. It will be at the negative end here, and it will be at the positive end here. If we are dealing with only a one-tail situation, then the point of rejection will be at just 1 point. So over here, if we expect our sample mean to be larger than the population mean, then we expect the difference to fall at the positive end here. And then if we expect our population mean to be larger than our sample mean, then we expect the difference to fall at the negative end. So this become the shaded portions are the points of rejection, the points of rejection. And then the non-shaded portions are the point of retention. Those are the areas that if our t observed falls, we will be retaining our HO. So we retain our HO if it falls here. When we are dealing with a two-tail, then if it falls within this range, we are going to retain our HO. If it falls here, we'll reject our HO, and when it falls here too, we will reject our HO. So using the t table, that's the critical value. Once we have our t table, and talking about the t table here, there are samples that have been uploaded on Sakai platform for you with illustrations and guidelines as to how to read the critical values using the degrees of freedom. So you obtain the appropriate t critical from the t table using the correct table depending on whether you are conducting a one-tail or a two-tail. Each of the tables that comes that you see on Sakai have two columns. One for if you are dealing with a one-tail hypothesis, and then the other if you are dealing with a two-tail hypothesis. So you have to pay particular attention to the research situation. You need to be very sure that this research situation involves a one-tail hypothesis or a two-tail hypothesis. Otherwise, you will read the wrong critical value. So once you pay attention to that, you need to also select your alpha level. And usually in a research situation, that will be given to you. And let me say it again here, that if the alpha level or the level of significance is not given to you in any research situation, then you go by the social science convention. You select 0.05. Use 0.05. So once we have one tail or two tail, and then we have our chosen alpha level, then all that we need to do is to get our degrees of freedom. And we said the degrees of freedom, if you are dealing with a one sample t-test, becomes n minus 1, where n refers to the sample size. So if you are dealing with a sample size of 20, then your degrees of freedom will be 20 minus 1, that will be 19. So you have to look for the row that goes with. The row that will be on your left will be the degrees of freedom, and then you have to select the 1 tail or the 2 tail and the corresponding alpha level, and then you get your T critical value. Now let's have a quick work example here. Use the following data set and conduct a 2-tail test to test if the population mean is equal to 12, if the population mean is equal to 12. So here we have the data here. You can see from the first row 6, and then the last one to 6. So we have a sample size of 18 over here. So what do? We have to state our HO, and here is a 2-tail. So our HO will state that our population mean is equal to 12, and then our H1 or HA will state that our population mean is not equal to 12. We choose our 0.05 since no specific alpha level has been given to us, so we go by the social science convention 0.05, and then we set the conditions. In setting the conditions, we need to rate our T critical. We need to rate our T critical. And here, as we can see, the sample size here is 18. There are 18 cases here. So 18 minus 1 will give us 17. So degrees of freedom will be 17. So if you go to the T table, the T statistical table, and then you select the degrees of freedom of 17 against an alpha level of 0.05 for a 2-tail T test, you get a critical value of 2.110. 2.110. So that is what we are going to use to set our decision rule. And remember, it is 2-tail, so the point of rejection will be, one will be at the negative end of the curve, and then the other will be at the positive end of the curve. So this is our decision rule. We are going to reject our HO if our T observed is greater than the positive of the critical value. That is, if our T observed, the one we are going to calculate, if it is greater than positive 2.110, and we also reject our HO if our T observed is less than the negative of the critical value. That is negative 2.110. So that is the decision rule that we've set over here. Now we have to compute our T observed, and we have it here. That's the formula for the T observed. This is the formula. So we have the mean over there, that is 13.67. If you add all these numbers and you divide by 18, because we have 18 cases, that will give us 13.67. So we subtract our population mean, which is 12, is given over here. We subtract the population mean of 12 from it, and that will give us the 1.67, and then we have the standard error of the mean based on the sample that is given as 0.380. So we divide it, and that gives us the 4.40 that we have over here. So now we have our T observed to be 4.40. So what we have to do at the next stage is to compare this 4.40 to the decision rule that we've set over here and decide whether we have to retain our HO or we reject our HO. And as we can see over here, this 4.40 is positive, so we have to look at the positive end of the decision rule. So we have to compare it to this, and we can see clearly that 4.40 is greater than the positive critical value. So since 4.40 is greater than 2.110, we have to reject our HO, because that is the condition we've set over here. If that happens, if the T observed is greater than this, then we have to reject our HO. So here we are rejecting our HO. That's the decision we are taking here. We are rejecting our HO. And rejecting HO means that this hypothesis is not the case. So which means that it is not the case that the population mean is equal to 11. So we quickly conclude that the population mean does not equal to 11. So that is how it works. Let me restate here that in an examination where you are asked to show full working in hypothesis testing, you need to go through the 6 steps that have been highlighted in section 2. You first have to deal with the choice of test, and you give reasons why you are selecting the specific test. You state your hypothesis. You state both your HO and your H1. You state them in statement form, and then you symbolize them. And then you set your decision rules. You do your computation step by step, and then finally you take a decision. And the decision that you will be taking here will be based on the outcome of your computation and the decision rule that you've set. And then finally you give us the interpretation of the decision that you have taken. For example, if here you have stated that HO should be rejected because the T observed is greater than the T critical, what is the interpretation? Does it mean that the mean of the sample is equal to the population mean, or it means that the mean of the sample is greater or rather smaller? That is the interpretation that you need to give us. So you need to follow these 6 steps when you are asked to show full working steps in hypothesis testing. And this applies to all the tests, not only the Z test, not only the one sample T test, but all the other tests that we'll be looking at: the independent T test, the correlated T test, the one-way ANOVA, the correlations that we'll be looking at. The same steps need to be applied in dealing with a full working steps. Now let's move on to look at inferences about the mean of 2 populations. So now we are done with instances where we have drawn a single sample from a single population. Now we are going to look at situations where we have drawn 2 samples, each of them coming from different populations. So here we have 2 different samples of participants being compared on a single dependent variable, or can have an instance where we have participant scores that are being measured under 2 conditions of the same independent variable. So condition 1 produces sample mean, and then condition 2 also produces another sample mean. So here we are dealing with 2 situations. For example, we have, let's say in an examination in statistics, we want to compare the performance of males and females. These are 2 different populations. So if we have a group of males, they will definitely be coming from the population of male students. And then the female sample will be coming from the female population. So these are 2 different groups that we have here. So those are the instances that we want to look at. And then we can also have a situation where we want to compare the performance of maybe one department against the other and stuff like that. These are the instances we are talking about here. So the parametric test procedure for determining whether the results of 2 sample experiment are significant is what we call the 2 sample T test. So where we are dealing with 2 samples, then we'll be using 2 sample T test. And there are 2 versions of the 2 sample T test. One is the independent sample T test, or simply the independent T test, and then the other is the correlated samples T test, or simply the correlated T test. The correlated T test has other names. It's also called the matched T test. It's also called the paired T test. It's also called the dependent T test. So take note of that. It has other names. So we'll first look at instances where we have to use the independent T test, and then later we'll also get to know instances where we have to use the correlated T test. So now let's talk about the difference between the means of 2 unrelated populations. So we are dealing with the independent T test. So here we are collecting 2 sample means and finding out how big the difference is between their means. So for example, we want to find out the performance of male students and female students. So on what is the difference in their average performances. Are males performing better than the females, or the females performing better than the males? So the mean of this sampling distribution is the HO difference between the population means, which is 0. So here, what HO will be saying is that there is no difference between their means. And if there is no difference between their means, it means that if you subtract one mean from the other, you should get 0. And that is what the HO will be testing, that the difference between the two population means equals 0. So two completely different, or what we call independent groups of subjects that you want to compare to determine if they are significantly different from one another, then we have an instance of what we call the between groups design. So perhaps in a study you have two groups, experimental group and a control group, or you have one department, maybe the business school, performance of business school, and the performance of a psychology department in academic writing. So these are two different groups. And all that we are doing is that we want to compare the means of these two groups. That is where the independent t-test is used. Two different groups being compared on their means. So when do we use it? That's the illustration that we have here. When do we use the independent t-test? We said when we have two different groups. So you can see one population here, population of males, A, and then the population of females, B. And then we have picked a sample from the population of females. We have it here. We have picked a sample from the population of males. And we want to compare how the two performs. We want to compare how the two performs. So that is an instance where we will use the independent t-test. Remember, the name is independent. The two should be different. The two should not be related. They shouldn't have anything in common. Shouldn't have anything in common. You belong to a different group, I belong to a different group. So comparing the performance of Christians and Muslims, two different groups, there shouldn't be anything in common, males and females. Comparing the performance of students that are residents in Commonwealth Hall and students that are residents in Legon Hall, two different groups. There's nothing that is relating the two together. These are the instances where we perform the independent t-test. So what are the assumptions? Let's have the full assumptions. The first one, we've mentioned that the two groups should be independent. So the two samples, there should be two samples and the between group design. In other words, the two groups should be unrelated. They should be different from each other. And then two, the sampling distribution should be normal. The distribution should approach the normal curve. And then the third one, the independent variable should be measured on the interval or ratio scale. The independent variable should be measured on an interval or ratio scale. And then finally, the variances of the two groups should be equal. The variances of the two groups should be equal, or they should be what we call homogeneous. They should be homogeneous. So these assumptions or conditions under which we run the independent t-test are the reasons that you need to give when you select that you want to use the independent t-test. Your reasons for the choice of the use of the independent t-test should address these 4 points. Now let's come to the formula, the standard error of the difference. Now, we may conceptualize the standard error of the difference between two population means as the standard deviation of the difference between two sample means drawn from the two populations. Just as when we are dealing with the one sample t-test, we subtract the sample mean. We have the sample mean minus the population mean, and then they divided it by the standard error of the mean based on the sample. So here what we did in the one sample situation is that we subtract their mean, we subtracted their means, and then we divided it by the standard error of the mean based on the sample. The same principle can be applied here, because here you are dealing with two samples. So what we are going to do is that we are going to subtract the mean of one sample from the other. And then, remember, each sample will come with its own standard error of the mean. So the denominator will simply be the standard error of the mean of the first sample minus the standard error of the mean of the second sample. And that will simply give us the formula for the independent t-test. You subtract their means from each other, that to form the denominator, that to form the numerator, and then at the denominator we subtract the standard error of the mean of one sample from the other. So this, and if you simplify that conceptualization, this becomes the formula for the independent t-test. It becomes the formula for the independent t-test. So at the numerator you have the mean of the first sample minus the mean of the second sample. And then the down there, that's the denominator, we have the sigma of the x squared of the first sample minus the sigma of the first sample squared divided by the sample size of the first one. And then we do the same thing to the second sample. We find the x squared, the sigma of the x squared of the second sample, and then we find the sum of the second sample, and then we square it, and then we divide it by the sample size of the second sample. So that is what we have here. This part deals with the first sample, this aspect deals with the second sample, and then we have in a curly bracket here the sample sizes, and this deals with the degrees of freedom. So we have the sample size of the first one plus the sample size of the second one. Then we have the sample size of the denominator, we have the sample size of the first one multiplied by the sample size of the second one. And then we have in bracket here the degrees of freedom, which is the sample size of the first one plus the sample size of the second one minus 2. And that will give us the formula for the independent t-test. It looks quite long but very simple to work with, because in the first slide we have dealt with how to handle these sigma issues. We have dealt with summation notation. Let me say here that it should be noted that the sign when you are dealing with an independent t-test, whether you obtain a negative or a positive value, the sign, whether you obtain a positive or a negative value, depends on what is happening over here at the numerator. Depends on what is happening over here. Remember, you are just subtracting one mean from the other. It is not automatic that the group information that will be given first will form the first group, and then what will come second will form that. That depends on you, the researcher. So whichever group you decide to make group 1 and whichever group you decide to make group 2 will determine whether you get a negative value or a positive value. Will determine whether you get a negative or positive value. So getting a negative or positive value when dealing with independent t-test doesn't affect the decision that we make. It doesn't affect the decision that we make. The decision will be the same. Now, how do we get the degrees of freedom and reading the t-critical? Critical values for the independent sample, that's the t-critical, are determined based on degrees of freedom, the selected alpha level, and whether we are dealing with a 1-tail or a 2-tail situation. So the same information that we need when we are dealing with one sample. To read our t-critical, we need our degrees of freedom. We need the selected alpha level or the significant level. If none is given, then we pick 0.05 that the social sciences have adopted, and then whether we are dealing with a 1-tail or 2-tail situation. Now, the degrees of freedom changes slightly when we are dealing with two samples, when we are dealing with two independent samples. Remember, in the one sample t-test situation that we have dealt with, we said the degrees of freedom is n minus 1. Here we are dealing with two samples, and the two samples are different. So our degrees of freedom will become n minus 1, which is for the first one, plus n minus 1, which is for the second one. So we simplify this, and then sometimes we state it as n1 plus n2 minus 2. Because here we subtract 1 from it, we subtract 1 from it. So at the end, we are going to subtract 2 from it, and then we'll be adding this and that. So that becomes the degrees of freedom when dealing with two independent samples. In a two-tailed t-test of independent sample, we will be rejecting our HO if our T observed is greater or equal to the T critical, or if our T observed is less than or equal to the negative of the T critical. So the same principle that we follow when we dealt with a one sample t-test is the same decision rule that we have to apply here when dealing with the independent t-test, because remember both are t-test. So the same principle that is here. So the degrees of freedom, as I said, we can simplify it to be this, n1 plus n2 minus 2. And that will give us our degrees of freedom, which we will need to read. So the computed, at the end, the computed value of T from the formula is referred to the T tables with the appropriate degrees of freedom under a specified decision rule, and the decision is taken whether HO should be retained or HO should be rejected. So here the same thing, we use the formula and compute for the T value, and that T value becomes the observed value or the computed value. And we are going to compare this to the critical value that we have used to set the decision rule, and then we decide whether our HO should be retained or the HO should be rejected. So how do we state our hypothesis when we are dealing with the independent t-test? First, let's look at a two-tailed situation. For a two-tailed situation, remember we have two means, the mean of the first one and the mean of the second one. So what we'll do is that our HO will state that if you subtract the population mean of one of the means from the other, the result will be 0. Because remember, HO always says that things are just the same. Nothing interesting is happening. Any difference that you see is due to chance, is negligible and can be ignored. So our HO here will state that the mean of the first one minus the mean of the second one will be 0. And then our H1 will state that the mean of the first one minus the mean of the second one will not be equal to 0. Will not be equal to 0. So remember, we can equally mathematically express this. If there's 0 here, we can send this to this side so that our HO can also state that the mean of the first group is equal to the mean of the second one. And then our H1 can also state that the mean of the first group is not equal to the mean of the second one. That is also another way of stating our hypothesis where we are dealing with a two-tailed test. So HO implies both samples represent the same population of scores. H1 implies that the means from our condition each represent a different samples, a different population of scores. Now let's look at it here where we are dealing with a one-tailed situation. That's a directional situation. Here the statistical hypothesis for a one-tailed test of independent samples are stated as follows. So here, remember we talk about one-tailed and two-tailed. We said one-tailed is where we have given it a direction. We are sure where it will be. So when it comes to one-tailed, then our focus will be that we'll be specific as to whether the mean of the first one will be bigger than the mean of the second one, or the mean of the first one will be smaller than the mean of the second one. We will be specific as to where the difference will be, which one will be bigger than the other. So that is what we have here. So here, somebody will be interested, a researcher will be interested. That is, if we expect that, if you expect the mean of the first one to be bigger or larger than the mean of the second one, then our HO will state that the mean of the first one minus the mean of the second one will be less or equal to 0. Will be less or equal to 0. And then our H1 will state that the mean of the first one minus the mean of the second one will be greater than 0. That is where we expect the mean of the first one to be greater or larger than the second one. That is how we state it. And then where we expect the mean of the second one to rather be bigger or larger than the second one, then our HO will be that the mean of the first one minus the mean of the second one will be greater or equal to 0. And then our H1 will state that the mean of the first one minus the mean of the second group will be less than 0. So that is how we state our hypothesis when we are dealing with a directional situation. That is how we state it. So some few points to note when we are dealing with a one-tailed test. First, we need to conduct one-tailed test only and only when we can confidently predict the direction that the dependent score will fall. If you are not sure as to where it will fall, whether one will be bigger than the other, then you don't go running a one-tailed test. And then 2, we also have to decide which of the X, which of the sample means and the corresponding population mean is expected to be larger. Which of them do we expect to be bigger than the other? And then we have to decide by convention which condition we want to subtract from the other. As I said, it's left to you, the researcher, to decide which of the sample mean will be subtracted from the other. There is no rules about that. So you have to decide. And then the next thing you need to do is to decide whether the difference will be positive or negative. Once you've done that, then you create your H1 and then your HO to match the prediction that you are expecting. You locate the region where the rejection will fall, you run or you compute the t-test, and then you compare it to the region where it will fall, and then you decide whether your HO should be rejected or your HO should be retained. So let's have a quick work example here. So using the following data set, conduct an independent sample t-test. Here we are asked to use alpha level of 0.05 and a two-tailed test. So we have the sample 1 here, we have the scores, we have 9 of them here, we have sample 2, their scores are here, we have 9 cases over there as well. So let's see. Now going through, you have to go through the 6 steps in doing that. But what I will do here, I'll just summarize it and give you the t-value, and then we'll look at how we take the decision. So here, if you compute the t observed, that will give us negative 0.285. Negative 0.285. But students are advised to use this formula to compute the formula for the independent t-test to compute this work example and check the answer to what has been summarized here. So we have negative 0.285. So let's come to it here. The t critical for the work example, there are 9 cases in each of them. So here 9 plus 9 will be 18 minus 2, that will be 16. So we have our DF to be 16 with alpha level of 0.05 for a two-tail. If you read, the t critical will give you 2.120. So here our decision rule will be that we reject our HO if the t observed is greater than the positive of the critical value, or we equally reject our t observed. We equally reject our HO if the t observed is less than the negative of the critical value. So here you can see that the t observed here, which we have obtained, that is negative 0.285, is actually less than the negative of the T critical. So because T observed of negative 0.285 is not beyond the negative critical of T observed, it does not lie within the rejection region. And so here we will retain our HO, because this value is actually bigger than this. It's not less, it's bigger than that. So here our decision will be to retain our HO. We are going to retain our HO. So that is how we work out the independent t-test. Once we get it, then we look at it. Does it fall? Is it less than this value? Because it's negative. Once we are getting negative, then we concentrate on the negative side of the normal curve where we have to reject. And so comparing this to this, we can see that this is actually greater than that. And because of that, our decision should be that we retain our HO. We retain our HO. Now let's look at the final one that we have to look at, the correlated t-test. As I said, it's also called the paired t-test or the matched t-test or the dependent t-test. And here we use it when we are making inferences between the means of two related samples. So if you look at it clearly, the correlated t-test is just the opposite of the independent t-test. We use the independent t-test when we are comparing the means of two unrelated populations. And here we see that we use the correlated t-test when we are comparing the means of two related populations. So the question then is, how would the two populations be related? The two populations can't have the relationship established between them at three levels. One is where we have what we call within subject design, and then two, where we have what we call match group design, and then three, where we have identical twins design. So let me explain this quickly. Within subject design is where we have the same subject being measured twice on the same dependent variable. So here what is happening is that we have the same subject serving as their own control. So if you want to run an experiment, let's say, for example, we want to find out the effect of alcohol on driving mistakes or errors that people commit on the road. So we decide to sample 50 drivers and we ask them to drive without taking in alcohol. So we look at the kind of mistakes that they commit on the road. So each time they commit a mistake, we tick so that we know the total number of mistakes we've committed. Then, after they've done the first driving, we brought them back again in the afternoon, this time giving them some level of alcohol to take. And then we ask them to go to do the driving again. And then we find out the kind of errors that they commit again. So here we have the same participants being measured twice on the same dependent variable, driving errors. The same participants went through the condition of driving without alcohol. This time they've gone through condition of driving with alcohol, being measured twice. So we have a within subject design. So here you can see two scores seems to be coming from two groups, but the two groups are actually the same participants. So we have a within subject design. In that case, we can't use the correlated t-test. We assume that the scores can be reduced to a single population and computed. And then we also talk about matched groups. Sometimes when it is very difficult to control certain factors, what we have to do is that we make sure that all characteristics and variables that could affect the dependent variable that is of interest to us, we make sure we control it ourselves in a research design. For example, if you are doing a study where we want to look at the performance of students, and we selected some students to be in group A and some students to be in group B, we want them to be equal so that no other variables will be different from the other group to the other, from the group 1 to the second group. So for example, if we pick a student in group A that is in level 300, age 28, is a male doing psychology, and is in Akwafo Hall, if we have such a person in group A, we make sure when you come to group B, there is another person who is in level 300, who is also age 28, who is also doing psychology, and who is also staying in Akwafo Hall. So what we are doing is that we are matching the participants in one group to the other on all the relevant characteristics that will affect our dependent variable. So we are kind of trying to create some artificial, identical situation among the participants. When we have such a matching being done, then that could permit us to use the correlated t-test. The final instance where we can also use the correlated t-test is where we have identical twin study. We all know that identical twins have the same genetic makeup and the same physical expressions. So when you have identical twins and you separate them, one pair goes into group A and the other pair goes into group B. So if you have 20 pairs of twins, you have 20 of them in group A and then 20 of them in group B. In that instance, any twin that you pick in one group, the other pair is in the other group, and because they are genetically and physically the same, we assume that the two are related. So that will permit us to also use the correlated t-test. So these are the instances that can create the relationship that we are talking about between the two populations. So clearly, to summarize, what I'm saying is that when do we use the correlated t-test? We use it when you have two measures taken on the same subjects in the case of the before and after research design, which is very common, where participants are serving as their own control. And then also when you have two separate samples, but the subjects in each are individually matched so that they are similar in each group. And then when we have identical twin studies. So these are the three conditions that can permit us to run the correlated t-test. So let's quickly look at the assumptions underlying the correlated t-test. One, already we know that the samples should be related, and we talk about the three instances that they should be related. Now the next thing is that the distribution should also be normal. It should follow the normal curve. And then the dependent variable, the DV, should be measured on an interval or ratio scale. Should be measured on an interval or ratio scale. So these are the assumptions that have to be met for us to run the correlated t-test. To run the correlated t-test. Now let's look at an example here, an example of a before and after pairing using the same subjects in each paired sample. So we have twins here that have been paired. We have the first pair, they are here. We have 4 of them here, and their scores over here. So an example of a paired design in which the actual subject in each sample are different but are matched for characteristics which could affect the dependent variable. Now, how do we compute the correlated t-test? How do we compute the correlated t-test? First, we need to compute what we call the standard error of the mean for the two related groups. And that's the formula that we have on the board here. Now, the formula on the right hand here is what we need to compute the correlated t-test. What we need to compute the correlated t-test. And the numerator here is sigma d. And the question is, you can say it is d, that is the new symbol that is appearing here. So what is the d? The d is simply the difference between the scores of the first group and the scores of the second group. And here I'm not talking about the mean, I'm talking about the raw scores of the participants in the first group and the raw scores of participants in the second group. We subtract them. Remember, we said the two groups are related, so we assume that the two scores are coming from the same participants. So what we have to do is that we are finding out the difference in the scores for each participant. So if For the first time that the scores were taken, the person has 20, and this time the person has 25. So we have a difference of 5. Subtract one from the other. So that is what will give us the D score. That's the difference in score. Difference in score. So at the numerator here, we find the sum total, the sigma of the D. And then when you come to the denominator here, we are going to find the square root of all that is here. And we can see n here, which is the sample size, and then sigma D squared. So D squared here means that when we find the difference between the first raw score and the second raw score, we square it. And then at the end, we add them up, we sum them up. And here we find the same thing, that is here, sigma D, the sum of the difference, the total of the difference, we square it up. And then we divide everything, the sample size minus 1. The sample size minus 1. So that is the formula that we need to use to compute the correlated t-test. So the computed value, once we've computed it, the computed value of t, which is also called the t observed, will be referred to the t table as we have done in the other test. We'll compare it to the t table under a specified decision rule with a degrees of freedom. And here the degrees of freedom that we need to use for correlated t is n minus 1. And once we've done that, we compare it and then we decide whether our HO should be retained or our HO should be rejected, depending on whether the observed value is greater than the critical value. So how do we state the hypothesis when it comes to the correlated t-test? It's just the same thing as we do in the independent t-test. When we are dealing with a two-tail situation, then our HO will state that the difference in the mean of the two groups will be equal to 0. And then our H1 will state that the difference in the mean of the two groups will not be equal to 1. So this is simply the mean difference. And then when we are dealing with one tail, depending on where we expect it to be, where we expect the difference to be, whether we expect the scores of the first, we expect the mean of the first score to be bigger, or we expect the mean of the second scores to be bigger, will determine whether we state it this way or we state it that way. So here our HO, that is where we are expecting the mean difference to be bigger. We state that the mean difference will be greater than 0. And then the HO will state that the mean difference will be less or equal to 0. And then here where we expect the mean difference to be less, then our H1 will state that the mean difference is less than 0. And then our HO will state that the mean difference will be greater or equal to 0. And the degrees of freedom, as I have said, when it comes to correlated t-test, it is n minus 1. It's just the same as we are dealing with a one sample situation. And it is so because in a correlated t-test, the two groups are equal. So we assume that they can be reduced to a single population of difference, can be reduced to a single population of difference. And that is how come the degrees of freedom also comes to n minus 1. And in the two-tail situation, this is the decision that we take when we are working with the correlated t-test. We will be rejecting our HO if our t observed is greater than the positive of the t critical. And we will also reject our HO if our t observed is less than the negative of the t critical. So you can see that the decision rule is just the same. Just the same. Once our t observed, if you are dealing with a two-tail, once the t observed is greater than the positive of the critical, you reject your HO. And if your t observed is less than the negative of the critical, then we will equally reject our HO. Otherwise, then we'll retain our HO. So now let's have a clear work example and then go through the 6 steps to see how it applies. So we have a question here, and this is, I think it's a past question, to determine the influence of early childhood social environment on emotional adjustment at adolescence. 16 sets of identical twins orphaned during infancy were obtained. For each twin pair, one member was placed in a foster home while the other member grew up with relations of their natural parents. At the age of 18, all twins were administered a self-report inventory that measured degree of emotional adjustment. That's DEA. Scores could range between 10 and 18, with higher scores reflecting better adjustment. So from the data in the table given below, so we have the data here, we have the scores that have been obtained from those that the twins that were raised in the foster home and those that were raised with their natural parents. So the question then here is, from this given data, did the type of early childhood social environment have any influence on the emotional adjustment of twins at adolescence? Does it have any influence on the emotional adjustment of the twins at adolescence? So look at the question. Clearly, let me ask, is this a one-to research situation or a two-to research situation? Is the question saying that those raised up in a foster home will be well adjusted than those raised up with their natural parents? Or did it say that those raised up in their natural parents will be well adjusted than those raised up in the foster home? No, that is not. We can't deduce that from the statement here. So clearly, this is a two-tail situation. This is a two-tail situation. So let's see how we approach it. So we go step by step. This time we are going to use all the 6 steps to illustrate what will be required of you if you are to show full working steps. So step 1, that's the choice of test. So here, what have we been given? We have been given 2 sets of scores that are correlated with each other. The 2 populations evolved. So we have 2 scores, and we are saying the 2 scores are related because they are coming from identical twins, one pair in one group and then the other in the other group. So here the 2 populations involved could be reduced to a single population of difference, which will be called the D scores. We can also assume that the distribution of difference score is normal in shape. And then we can further assume that the scores on emotional adjustment have at least been measured on an interval scale. Here we are given that the scores ranges between 10 to 80, so we can assume that it is on an interval scale. So with these conditions identified, the most appropriate statistical test to use to answer the research question is the matched or correlated t-test. So clearly you can see what we have done in step 1. We have identified the key features which forms the basis for which we are selecting the specific test to use. And then step 2, which is the statement of hypothesis. And here I said we need to state the hypothesis, both H1 and HO, in statement form, and then we also symbolize them. And in doing that, we have to pay attention to whether we are dealing with a one-tail or we are dealing with a two-tail situation. So here, let's see what we have here. We are required to determine whether or not the type of early childhood upbringing has an influence on emotional adjustment at adolescence. The hypothesis, therefore, is two-tail, since we are not told the direction of the possible influence of early childhood social environment on emotional adjustment at adolescence. So let UD represent the population mean of difference. And once we've defined this symbol, we can now state our H1 and HO. Then the null hypothesis and the alternative hypothesis may be stated as follows. HO, the type of early childhood social environment has no significant influence on the emotional adjustment of the orphaned twins at adolescence. And here is the symbolization. The population mean, the difference of population mean will be equal to 0. Mu D will be equal to 0. And then our H1 will state that the type of early childhood social environment will have a significant influence on emotional adjustment of the orphaned twins at adolescence. So here the mu D will not be equal to 0. Going to have some influence, so the two will not be the same. So that is how we state the hypothesis. And then step 3, which is the decision rule. And here, to get the decision rule, we need the critical value. We need to read that from the T tables. And before we read that, we need certain key information. One has to do with the level of significance, whether we are dealing with a 1-tail or 2-tail. And then also, we need the degrees of freedom. So we need these 3 key information for us to read the critical value and then set our decision rule. So here, since we have not been given any level of significance, we go by the social science convention. So here, given 0.05 level of significance and a 2-tail correlated t-test with a DF of n minus 1, which is equal to 16 minus 1, because we have 16 participants in each of the groups. So that's 15. The critical value of t from the t table. So if you read DF of 15 for a 2-tail with 0.05 level of significance, you get a critical value of plus or minus 2.131. So this is what we are going to use to set our decision rule. And remember, we are dealing with a 2-tail. So the point of rejection will be at 2 places. It will be on the left, and then it will also be on the right. So we come here and remember what we have been stating all the time, that we will reject our HO if our T observed is less than the negative of the T critical, or if the T observed is greater or equal to the positive of the critical. So that is what we need to state here. So reject HO if T observed is less than or equal to the negative of the T critical, that's negative 2.131, or if T observed is greater or equal to the positive of the critical, that's 2.131. And then otherwise we have to retain our HO. So that when we are dealing with 2-tail, then the point of retention of HO becomes a range if our T observed is greater than the negative of the critical, and if it is less than the positive of the critical. So that's our decision rule that we've set over here. Then we've come to the computation. And the computation, we need to select the appropriate formula. We need to select the correct formula for the specified test. So here, with the usual notation, the computational formula for the correlated t-test is given as T equals sigma D divided by the square root of n sigma D squared minus bracket sigma D squared divided by n minus 1. So once we've stated the formula here, we now go step by step for us to work it out and then arrive at the final answer. So here, there's a note here, compute all the necessary summations and input into the formula. You need to show working. In other words, you need to go step by step for the examiner to be convinced that you did the computation yourself. And the key thing you have to do here with this formula is just to find the D, subtract one scores from the other, you square it up, and then you sum it up. So when you do that, our sigma D will give us 66. The rest of it are here. Our T observed will be approximately 2.224. 2.224. So this comes to 2.224. Remember to correct it to 3 decimal places. So that we come to step 5, the decision. This is where we take a decision as to whether we retain or reject our HO based on the information we have obtained from step 4 and the decision rule we have set in step 3. So here they are saying that referring the T observed, which is positive 2.224, to the decision rule in step 3. And what is the decision rule that we have in step 3? concerning the positive. We are saying that we will reject our HO if our T observed is greater or equal to 2.131. What we have obtained now is 2.224. It is greater than this, so we need to take the decision to reject our HO because it satisfies this condition. So here, referring the T observed of 2.224 to the decision rule in step 3, we note that the 2.224, which is our T observed, is greater than the T critical, 2.131. Therefore, HO is rejected at the 0.05 level of significance. So here we have rejected our HO. That is the decision we have taken. So we move to the next and final step, step 6, the interpretation. What is the meaning of rejecting our HO? What is the meaning of rejecting our HO? Remember, our HO is this, that the type of early childhood social upbringing has no significant influence on the emotional adjustment of orphan twins at adolescence. And we are saying we are rejecting this. So this is not the case. Once this is not the case, then what will be the case is our H1. So our interpretation should be our H1. So let's say, so here we are saying that at the 0.05 level of significance, a significant difference exists between the emotional adjustment scores obtained by twins raised by foster parents and those raised by family relations. So that is what we are saying, because our HO says there's no difference. Here, once we've rejected our HO, it shows that there is a difference between them. Therefore, our conclusion will be that the type of early childhood upbringing, the type of early childhood social upbringing had a significant influence on the emotional adjustment of the twins at adolescent. So that will be our conclusion. So that is the interpretation that we have given. So now we have gone through the 6 steps and we've seen how to solve a typical examination question. A very important point which I've said earlier, that these same steps that we have used, that is what we need to go through in answering any full question that has been asked, be it a Z-test, T-test, independent T-test, correlated T-test, one-way ANOVA, or any of the correlations that we will be looking at. So we have come to the end of this lesson. The reference lists are here. And I hope you've learned a lot. You should be able to try your hands on some of the research situations that involve making inferences about a single population, whether the population standard deviation is known or not, and then also making inferences about 2 populations, whether the 2 populations are related or not. In the next section, we will be looking at making inferences about research situations that involve more than 2 populations, That means we will be dealing with one-way ANOVA in the next section. Thank you.